Next, we have Sébastien Reymond from KU Leuven that's going to present a talk called Black Holes, Moduli Stabilization, and the Swampland. So, without further ado, Sébastien, the screen is yours.
Thank you very much. Thank you everyone for being here. And thank you to the organizers for allowing me to talk about this recent work I have with Matilda Delgado and Thomas van Riet. So, as you may know, and as was clearly explained in the previous talk, black holes seem to be key probes into quantum gravity. So many Swampland conjectures or principles like no global symmetries or the fact that gravity should be the weakest force can be understood from black hole thought experiments, in addition to top-down constructions. Moreover, black holes seem to be quantum in nature. They have an entropy that seems to count microstates. And so for all those reasons, it's clear that black holes have something to tell us about quantum gravity. Now, specifically in the context of string theory, black holes have been mostly studied in well-controlled, but not, I would say, realistic situations. So for example, in the context of holography, take the canonical example of ADS5 cross S5. Black holes have been studied in this context a lot in very interesting works, but it's clear that the S5 size is comparable to the ADS5. So you have a 10-dimensional theory, not really a 5-dimensional one. And in our universe, it seems that there's 4 large dimensions and not more. And so for a more realistic construction, we would like to have scale separation. Moreover, in a lot of those well-controlled examples, there is no or only partial moduli stabilization with a lot of massless fields around, which we also do not observe in our universe. So how about black holes in more realistic compactifications? Well, it turns out that as far as we can tell, that has not been studied much in the literature so far. So to the best of our knowledge, we know of 2 papers, one of Green, Silverstein, and Starr from 2006, which is more of a bottom-up approach, and one by Danielson, Johansson, and Larfers, which is a type 2b construction. But other than those two, there hasn't been much work. So the question is kind of still open. What can they tell us? Could they tell us something about the compactification itself? Could we learn some physics from it? So this is sort of a very big question to ask, but today I will go with a specific angle of attack at this question. So first, let me explain how this angle of attack works for black holes in non-realistic setups that I mentioned before. So the idea that we're going to use is that the horizon of extremal black holes are attractor points for moduli. So if you have some modulus phi, its value at the horizon, phi h, is fixed by the black hole charges independently of its value at infinity. And one result in a context with those moduli is that large black holes can actually probe large distances in the moduli space. So an equation delta here is the distance traveled by the field, so the difference between its value at infinity and its value on the horizon. And that distance grows with the log of the black hole mass in Planck units. And as I'm sure many of you know from the distance conjecture, when you travel large distances in moduli space, you have towers of states becoming light, and so the cutoff of your EFT goes down, and therefore you have a possibility of the EFT breaking down at the horizon of those black holes. Now, maybe for you, this is a bit surprising and a bit puzzling because large black holes famously have quite low curvature at horizon scales. The biggest black holes we're aware of, and say in the center of galaxies, supermassive black holes, we think for sure at the horizon scale, it's almost flat space. There's very low curvature and very low energy density there, except for, of course, accretion disks, but whatever. So how could they probe the UV? Now, we believe that this effect that the larger black holes can probe large distances comes fundamentally from the fact that you have moduli around. So this is our guess, here explained in a picture. Since the moduli are massless, they're quite easy to displace since they have no mass. And therefore, you're in the setup on the left. You have the field profile of the modulus or the field phi. It can be anything at infinity, but at the black hole horizon, it's fixed by the black hole charges. And generically, if you travel a large distance, you might have UV physics coming down. Now, how does this picture change when you stabilize the moduli when they have a mass? That's the picture on the right. So now the value at infinity is fixed at the minimum of the potential. And as you approach the black hole horizon, this value of the scalar might change a little bit, but as long as there's no huge energy densities at the horizon, normally it should not move by much. This is essentially an EFT reasoning. If the scalars have a mass, the black holes should not be able to do much unless they have very high horizon scale curvature. So this is the intuition. I should also say here, of course, if you're on the case on the left, of course, you can always sort of tune the value of the modulus at infinity to be exactly that of its attractor value, but that's sort of fine tuning. And for generic condition at infinity, you would still expect to have a non-trivial profile. Anyway, this is the intuition, but should we check it? So the idea is that we check this intuition using a very simple toy model, which is very similar actually to the one in the previous talk. So this is Einstein-Maxwell theory with a massive dilaton. This is a model that was originally studied by Horn and Horowitz. And the reason why we study this is essentially describing the long-range physics in our universe if you believe that the fine structure constant comes from the VEV of a heavy field. So here, think of the mass of the dilaton as some UV scale, way above the standard model scale, say. And when you're below that scale, you can integrate out the dilaton, and that sets the fine structure constant, so the coupling of F squared. Now the question is, in this theory, can black holes drag the scalar phi far from its minimum? So the way we approach this problem to make it as simple as possible is to look for ADS2 cross S2 solutions of that theory, which you then think of as the near horizon of an extremal black hole. Then when you have this solution, this ADS2 cross S2 solution, the dilaton will have a specific value, which is the value at the horizon, and then you can deduce the field space distance traveled. So how does it work in practice? Let me first show you how it works when m equals 0. When m equals 0, you get a set of equations that describe this ADS2 cross S2 vacuum. The equations depend on this function VBH, the black hole potential, that depends on the black hole charges and details of the theory. This is quite a generic result. When I say details of the theory, I mean specifically how the scalars couple to F squared and F wedge F generically. Now, this is essentially directly showing you the attractor mechanism. So the first equation tells you that the value of the scalar at the horizon is set by extremizing the black hole potential. And the second equation tells you that the black hole potential value sets the ADS2 and the black hole or the S2 scale. Very good, but this is a bit abstract. So how does it work specifically for Einstein-Maxwell dilaton? Well, there you have this explicit function for the black hole potential. It's quite simple. Q and P are electric and magnetic charges. This e to the a phi is exactly the coupling to the F squared that I showed in the action before. And there you can see the attractor mechanism at work. The scalar value at the horizon is given by a ratio of charges, so independently of the value at infinity. And the black hole size is now a product of the charges. So here you see, for Q much larger than P, you do get those large black holes that can probe large distances in field space, as in the papers I mentioned before. Now, the question for us here is, how does the presence of a scalar potential, how does the presence of a mass for phi change the story? So here I'm rewriting the equations for m equals 0, and I'm showing you how they change when you add the scalar potential. So you see the first equation tells you that now there's competition between the black hole potential and the scalar potential. So determining the value of the scalar in the ADS2 cross S2 vacuum will be a bit more non-trivial than before. The second and third equation tells you how the black hole size and the ADS2 size are related to the scalar potential and the black hole potential. Very good, but so the question now is, how much does the scalar potential change the attractor story? And can we still probe large field distances? So as you may guess, there's two length scales that appear in this problem. There's the black hole size and the Compton wavelength of the scalar. So we essentially study two regions. The first is when the black hole is large compared to this Compton wavelength of the scalar. In that context, you expect very little scalar displacement because the curvature scales will be very low compared to the mass of the scalar at the horizon. Now, the opposite regime is what we call small black holes, where now the scalar is essentially almost massless. So it's very easy to displace, and you expect a similar behavior as in the attractor story. Now, I should say, if you think of m, the mass of the scalar, as a UV scale, say above TeV scale, then every black hole in our universe that we know of so far are large black holes. They're much larger than inverse TeV. Okay, so does our intuition work? Well, you can compute, you can solve those near horizon or ADS2 cross S2 equations perturbatively and a small parameter in both cases, and the intuition completely works. So for the large black hole case, the value of the dilaton at the horizon is much smaller than 1. It's actually suppressed by the product m times RBH squared. And so you indeed get it, as in the picture on the right, a very small deviation from the asymptotic value. And here you get the opposite behavior as in the moduli unstabilized case. You get that the bigger the black hole is, the smaller the distance traveled, which makes sense from an EFT point of view. Now, of course, in the other regime, for small black holes, you only get a small correction to the attractor value. You see here that the value of the scalar at the horizon is still given by Q over P times a number that's very close to 1. Very good. So let me recap what I've said so far. What we observe is that without moduli stabilization, there exists black hole that have the following behavior. The bigger the black hole, the bigger the distance traveled. In the toy model, it's the opposite. The bigger the black hole, the smaller the distance traveled. And so from this observation, what we wanted to understand is generically, say in top-down or in string theory constructions, what criteria would lead to this second behavior. So here we hypothesize that you would need a genuine 4D EFT, so to be able to make the calculations, and then you need genuinely heavy scalars compared to the IR scales. Otherwise, a large black hole could still move the scalars. And so this leads us to the definition of a rigid compactification. So there's two parts of the definition. The first one is that you would like a scale separated vacuum. So you would want the extra dimensions, the KK scale, to be very small compared to the ADS scale. The second criterion is that the remaining scalars should be stabilized at a high scale compared to the CC scale, so that the mass of those guys in ADS units are much larger than 1. In this case, there should not be any UV physics at the horizon of large black holes because everything is, in a sense, very tightly stuck at the bottom of a potential. Now, as you may know, this is actually not so easy to come by in string theory. As far as we know, there's no example so far, but I'll get back to that. So in order to sort of understand what's going on from a more top-down point of view, we relax the second assumption and we get essentially the closest thing where we only require moduli stabilization, but not the stabilization at a very high mass. So we allow masses of order 1 in ADS units. And in this context, we'll pick a non-rigid model, an explicit one, and we will look for black holes with the property, the larger the black hole, the larger the distance, to see if the story from the moduli unstabilized case remains even with sort of light stabilization. So what do we need for this top-down example? We need scale separation and we need moduli stabilization. And importantly, we need a gauge field to charge the black hole, which couples to a stabilized scalar. So the specific example I want to talk about now is a two-way vacuum on the orbifold T6 mod Z4, which closely follows this paper of 2007 by Eel, Robinson, and Raza, and which is an example of a DJKT compactification. So what are the properties of this model? It achieves parametric scale separations. You can trust the 4D EFT in ADS4. And the remaining scalars are 6 complex scalars that have order 1 masses in ADS4 units. So with this, we meet the first criterion above. Now, what about the gauge field? Well, the gauge field comes from reducing C3 over an even 2 cycle. And the interesting thing is that it couples to only one complex scalar, T3, which is made of an axion U3 and a saxion U3. And the reason why we pick this sort of model is that you get this very simple expression for the black hole potential. It's written here. Again, Q and P are electric and magnetic charges. And interestingly, if you artificially set U3 to 0, this is exactly the potential I was talking about in the toy model. If nu3 is like e to the a phi. This is the same form as before. So very good. We have a black hole potential, but of course, we need to find now the scalar potential to observe the competition between the two. So how does that work? To make our life simple, we make a very simple flux choice for all the fluxes that entered this model, and we make everything be characterized by the four-form flux quantum M. For those familiar with the story of the JKT, this is the flux quantum that decides that leads to the scale separation. So when M is very large, you achieve scale separation, but I will come back to that. Now, since the vector field that we have only couples to T3, we would like a scalar potential V of T3. But as I said, the 5 other complex scalars would stay then in their cosmological minimum. So it's actually possible to reduce the problem to only one complex scalar. Maybe it's easier to understand this in terms of equations. For all the scalars that are not T3, you solve the F-term equations in terms of T3, so you get phi I of T3, plug that back in the potential, and you get sort of an effective potential for U3 and nu3. Now, this potential, unfortunately, I couldn't fit it in the slide. It's a ratio of two complicated polynomials, but okay, we have an explicit expression. We can work with it in Mathematica. It's just a bit long. Now, the minimum of this potential is given, it sets the ADS4 scale. And you can see here that the ADS4 scale squared goes like m to the power 9. So that's the sense in which scale separation happens. So as m becomes very large, the ADS4 scale becomes large. At the same time, the internal dimension size also becomes large, but slower as a function of m, and so you achieve scale separation. So we have reduced the problem to just two real fields. Now, the job is to solve the ADS2 cross S2 equations and try to see what the distance traveled is. Now, I won't talk too much about the details here, but I just want to highlight a specific class of solutions that we found. So for some choices of charges, we find the following properties at large M. Actually, out of the two scalars, out of the two real scalars that we had, U3 and U3, only one of them moves. So U3 is sort of constant along the flow. And nu3, the distance it travels is set by this, is given by this delta nu that is in the equation. And so the distance depends on the size of the black hole, RBH, in ADS4 units, which for a class of solutions goes like m to the alpha for alpha some number between 0 and 1. Since m is very large, this becomes very large, and so you get what we were looking for, a large black hole that can significantly displace a scalar from its minimum. This actually is the kind of black holes that Bushin was talking about before, the black holes that are larger than the ADS4 scale. Okay, very good. So we have an example of such a thing in top-down models that kind of realizes the behavior that happened in moduli unstabilized scenarios. So how do we think about this? Well, we distinguished two classes of theories, the rigid compactifications, where large black holes can never lead to large field displacements from an EFT point of view, and non-rigid compactifications, where you allow light scalars in ADS4 units, and in this context, some black holes can drag scalars very far from their minimum. So from this, I'd like to speculate, not conjecture. So we speculate that if, for whatever reason, UV physics is required at horizon scale of large black holes, then rigid compactifications are not allowed because everything would be so stuck that nothing can move at the horizon and you have no chance of seeing UV physics there. Now, the reasons for why you would want UV physics to happen, we remain agnostic about, but it could be because you would like some non-locality at the horizon to maybe solve some paradoxes, or you would like an explanation of microstates that goes beyond an EFT, or anything like this. We just want to say that UV physics at the horizon is going against rigid compactifications. But of course, this also is supported by examples in string theory. As I said before, they're very hard to come by in string theory, those rigid compactifications. So the first conjecture that goes in favor of this is this ADS moduli conjecture by Gautason, Van Hamelrijk, and Van Riet that says that the lightest scalar in this ADS vacuum cannot be parametrically heavy in ADS units. So that already goes against the second definition of what I call rigid compactifications. The second conjecture is the strong ADS distance conjecture that states that there's just no scale separation possible in SUSY ADS. Of course, the DGKT example I was talking about before is a counterexample to this conjecture, but of course, as you know, it's debated. So we stay agnostic. We just say if you would have such a conjecture, such a uh, compactification, such a scenario, then this is what we find. So because of both of those conjectures and because they seem very hard to combine in string theory, we speculate that rigid compactifications are in the swampland. So please, you're welcome to give us counterexamples and to tell us how this is wrong, but we'll be very, very excited to hear it. But now, before I finish, let me just get back to our universe. So our speculation is that light, dark sectors seem difficult to avoid from top-down constructions. This is also as an example, the dark dimension construction or scenario is one of those light-dark sectors. And if there is such a sector, large black holes could displace the scalar significantly. But of course, one complaint that you could have is that in our universe, there's no like close to extremal or very large charged black holes. But actually, our argument might not only work for charged black holes, maybe it works more in general. So this, I will just state an argument from Green, Silverstein, and Starr that states that essentially, generically, light scalars couple to fermions in the form, say, G of phi, psi bar psi. And this is quite similar to the coupling that we had between the scalars in the gauge field, G of phi, f squared. And so if there is such a coupling, you would expect a contribution to the scalar field displacement from a term in the black hole potential that depends on this fermion condensate. Now, the speculation is that possibly the collapse of stars, which are made of matter, made out of those fermion condensate, may significantly displace those light fields. So this is something worth investigating, I would say. So as an invitation, the Swampland seems to tell us that there may be light fields around. How do black holes move them? And could this be an observable effect in our universe? So finally, to conclude, what we know is that the distance conjecture tells us that UV physics can come down at black hole horizon if scalars have traveled a large distance. This was initially proposed in setups without moduli stabilization, and what we did is to try to expand it to cases with the moduli stabilization. So first, we studied a toy model where the moduli are stabilized, where the main result is that this matches our intuition. When the masses are high compared to the inverse black hole size, you can never probe large distances. This led us to define rigid compactifications, which are scale separated and where the scalar masses are much higher than the CC scale. But as I said, there's no top-down example so far. So then we looked at the next best thing, if you will, and we studied some black hole solutions in semi-realistic but non-rigid top-down scenarios for the first or second time. The main result is that for some black hole solutions, you still have this behavior. The bigger the black hole, the larger the distance traveled, as for the moduli unstabilized case. And we guess that this is because the scalar masses are order 1 in ADS4 units, and so they're not very heavy compared to cosmological scales. So maybe to finish, the punchline is that if for whatever reason you would like UV physics to come down at horizon scales, then it seems that rigid compactifications are in a swampland. And this is also backed up by the fact that there's, as far as we know, very few, if any, examples of rigid compactifications in top-down examples. So thank you very much for listening, and I'm done talking for now.